On a surprisingly warm January day in 1919, nobody expected a killer tide of molasses to wash over the city of Boston, Massachusetts. Even in retrospect, it sounds like a goofy myth. Despite its garishness, the Boston molasses disaster was, indeed, a disaster, with real, fatal consequences. From this catastrophic event, and the faulty engineering which caused it, we can glean several useful lessons on pressure, internal forces, and fluid dynamics. This is the Purity Distilling Company's Molasses Reserve, or at least it was. A giant cylinder which dominated Boston's North End. It emanated a sweet smell which permeated its surroundings. More problematic was its unenforced, untested cylindrical design. Despite its poor construction, Boston locals went about their daily lives unfazed by the loud groaning noises the tank made, or by the frequent molasses pools which leaked from its base. On January 15th, a police officer looked up to see the tank's rivets flying across the sky as it burst open, unleashing a viscous tide of molasses that killed some and injured many others. The danger of the fluid itself was multiplied by the heavy shards of exploded tank that followed. In analyzing the lead-up to the disaster, simple physics concepts illuminate the structural and environmental causes of the molasses flood. The tank is a standard model of Bernoulli's equation, demonstrating that pressure within the tank is directly related to the speed at which it flows through an opening. The slow leaks which initially poured out of the reservoir indicated a risky, but relatively sustainable internal pressure, and the high-speed explosion that destroyed it indicated an unsustainably high internal pressure. Unusually high temperatures may have exacerbated the tank's pre-existing structural problems. The day before, temperatures were in the single digits, but they rose into the 40s around the time of the tank's explosion. As temperatures rapidly increased, so did particle motion within the enclosed space, and, in turn, pressure. Additionally, the heat generated excess carbon dioxide within the tank, which further increased internal pressure in accordance with ideal gas laws. Looking at the equation, it becomes evident that as temperature rose, so did pressure, necessitating an increase in volume. This increase eventually occurred in the unfortunate explosion of the tank. What could have prevented such a disaster? Well, a redesign of the reservoir is an easy first step. Its tall, cylindrical design may have made molasses removal simple, but it also created unnecessary danger. In order to minimize internal pressures, the base of the tank should be enlarged and its height shrunk. Although this design would take up more physical area, the internal forces of molasses would be distributed more evenly and wouldn't add vertically to gravity to such an extreme degree. If changing the shape of the structure itself was not an option, then temperature controls could have helped. Considering that temperature changes contributed overwhelmingly to the explosion of the tank, a system of heating and cooling would sufficiently regulate pressure. Even the addition of simple vents would have helped significantly, removing excess carbon dioxide from the tank. Lastly, the simplest change Purity Distilling could have made was a simple change of material. Thicker walls, or perhaps a different metal, could have provided the structural integrity necessary to withstand the environmental conditions on that fateful day. Tragedies like the molasses flood are horrifying, but they are extremely helpful in the progression of technology and engineering. Today, we use and manipulate pressure in so many ways. From enormous water towers to airplane cabins, pressure and its effects have come under our control. Without events like the molasses disaster, we would not have been able to fix fatal problems and improve engineering in the long term.